Shinjini,
Huh.
maybe we can start, huh?
Okay. So good afternoon all. Welcome you to the second day of the online workshop on undergraduate physics experiments. So I'm directly going to the technical session. Our resource person for the first technical session is Dr. Makhun Lal Nanda Goswami. He is Associate Professor of Physics at Midnapur College, Medinipur. He is interested in physics project works. He has developed a number of physics experiments for the different workshops organized by his college and other institutions. Dr. Goswami will deliver his lecture on the measurement of the horizontal component of Earth's magnetic field and magnetic moment of a bar magnet using a magnetic needle. Over to you, sir.
Thank you, ma'am. Good afternoon, everybody. Actually, Dr. Surojit Chakraborty, sir, suggested the experiments which we have performed. The first one is to determination of Earth's horizontal component, magnetic field, Earth's magnetic field, horizontal component, Earth's magnetic field. And the second one is measurement of unknown resistance using Wheatstone-Bridge null measurement. Can I present now?
Sure,
Yes,
sir.
sir. Yes.
Is it visible?
Yes, yes. Mhm.
So actually the experiment is determination of Earth's horizontal intensity and moment of a magnet. The purpose of this experiment is to measure the magnetic moment of a bar magnet and the horizontal component of the Earth's magnetic field. Since there are two unknown quantities, M and H here, we need two independent equations containing the two unknown. So the first procedure will be ratio of two unknown, that M by H is a basic theory in every textbook. M by H equals to that 4 pi into T square minus H square the whole square by twice D 4 pi by mu 0 and that tan theta. Where M is magnetic moment of the magnet Twice actually the length between the pole and that is 0.85 into the actual length of the magnet, bar magnet. D is equal to the distance between the center of the magnet and the center of the magnetometer needle, and theta is deflection of the magnetometer needle. And the second is the product of two unknowns, and if we solve the two equations simultaneously, then we will get the value of H and M. And the time period, oscillation time period, if the bar magnet is hanging from a thread and twist around 10 to 20 degree from its equilibrium position and then release it, it should oscillate in angular simple harmonic motion. And twisting the string, we can use a clock or watch. That mobile phone can do this to time of 20 or 30 cycles, and we will get the time period, and the relation is well known. T is equal to 2 pi root over I by H, where I is moment of inertia, and the moment of inertia is related to the length of the bar magnet and the breadth of the bar magnet and the mass of the bar magnet. So mh equals to 4 pi square I by T square, and from there H square is equal to this. And if the distance between the center of the needle, magnetic needle, and the center of the bar magnet is much greater than the length of the bar magnet, then we can write this H square is equal to 4 pi square I by T square into this part, twice mu 0 by 4 pi D cube tablet. So from this relation, H can be calculated. Here Y is the perpendicular distance from the magnetic meridian, and X is the base distance from the center of needle. Actually, requirement is one bar magnet, scale, stopwatch, can be used by a mobile phone, slide calipers. If not, we can use ordinary scale. Balance and weight box is required, but mass of the magnet can be supplied, or we can measure in the laboratory, and one magnetic needle. So this experiment means the determination of the Earth's magnetic field, horizontal component of Earth's magnetic field, and the moment can be done by a different method, deflection magnetometer in the laboratory. This is a huge setup, or using tangent galvanometer Earth's magnetic field. can be determined. But in tangent galvanometer, there is also a number of apparatus: gradual compass, current carrying coil, reverse plate, power supply, ammeter or multimeter, like this. But sir suggested, or we can do this experiment by using a simple scale and a magnetic needle and a bar magnet. So if we have these magnetic needle, magnet, and a scale, or 1 meter or so, not 1 meter, but less than 1 meter is also enough thread for the hanging this bar magnet from the center of the bar magnet. We can measure the time period. So experimental setup is very simple. This is the experimental setup. We have the magnet, bar magnet, and a magnetic needle. This is a magnetic needle, and this is a bar magnet. So first, the mass of the bar magnet is measured with a balance. Length and breadth can be measured using slide calipers, or we can use the ordinary scale also. To find the time period of oscillation of the bar magnet, I said that twist the bar magnet after hanging by a thread around 10 to 20 degree from its equilibrium position. You can easily calculate the time period. Now we have drawn the perpendicular line on a A4 paper. Then the direction of the magnetic meridian determined using the magnetic needle. And we have placed a bar magnet perpendicular to the magnetic needle with the end pole of the magnet. This is here in the here. So if we move the bar magnet towards the needle, then there is a deflection in the needle, and mark the deflection of needle both sides and join the two mark point using pen or pencil. You will get the deflection, and we can measure the perpendicular distance y from magnetic meridian line, and base distance is x along the magnetic meridian. We can calculate tan theta. We can draw the curve tan theta versus 1 by d square, or cot theta versus d square, which is passing through the origin, and we can calculate the Earth's horizontal intensity using this equation 5. equation 5 is H is equal to pi by 2 ht twice mu 0 I pi d tan theta. And if we get the Earth's horizontal intensity, we can easily calculate the magnetic moment of the bar magnet by putting the value of that H in the expression of in the equation 3. So it is very interesting and important. We have done experiment, performed experiment in this way, but the caution is there. The magnetic needle should not be very close to the bar magnet. If once bar magnet is very close to the magnetic needle, then it is difficult to place a magnetic, difficult to find the magnetic meridian using this needle. And also we have to remove the ferrous materials or magnetic material from this table or some from the surroundings. This is actually the experiment. So we can do this experiment in our home if we have that magnetic needle and a bar magnet. We have scale, we have mobile. So this is one experiment we have performed. This is sir. Thank you. Sir, are you hearing?
Yes, yes, no problem.
Can I show the result?
Yeah, why not? Sure. I'm also interested to see.
This is the time period oscillation time period, and one result. Actually, I have taken data and find the result is around which one? Earth's horizontal intensity here is 0.37, 0.37 Ghosh. They are found.
So you have three data of distance versus tan theta, right? 11.6, 13.7, and
Yes, sir.
18.6. So you could have probably drawn a straight line of tan theta versus 1 by dq. That should be a straight line, right?
That should be a straight line.
Yeah. So that could also be done. What was your value of Earth's magnetic field, horizontal component?
0.376 Gauss.
Okay. And magnetic moment of the
534 alpha Gauss.
okay. So
Actually 0.39 given in the Calcutta Earth's horizontal component value.
but what about your place in Midnapur? You
I don't
know.
know. I have to search.
Okay, all right.
Calcutta is available.
I don't know whether there are any questions. Shinjini, are you there?
Yes, I'm there.
So,
Just let me check whether. Let me
yeah.
check the chat box.
Okay.
No, there is no question.
Okay.
No.
Okay, so I will make just one comment on this experiment. In
Sir.
undergraduate labs, I mean, probably all undergraduate labs have this experimental setup with a wooden base on which a big magnetometer is put in. I don't think there is any such need of using
This is
so.
a deflection magnetometer, sir.
Yeah, I
We
know.
have also laboratory in our
Yeah, I
laboratory.
know, but I mean, don't understand what is the purpose of so huge a system. I mean, you have to spend some 2-3 thousand rupees because of this wooden block only. So that job can very easily be done with a small needle of say it costs only 30 rupees. So very easily, I mean, this can be done.
Dr. Chakraborty,
Huh? Yes,
Dr. Chakraborty,
yes, yes.
I think the students should be told under what condition the torsional rigidity has been rather not included.
Torsional rigidity of
Has not been included in the expression for time period T.
I mean, the string should be twist free. That's all. I mean, there should be no twist. I mean, it should not be a metallic thread. It's just a cotton thread will be good enough. Because actually, the Earth's magnetic field will be the main cause for angular oscillations. So the thread
That,
shouldn't have any twist. That's all.
that's fine. That's fine.
Uh,
But even if we use the metallic wire, then I
mhm.
think we can get another experiment to be done as regards the torsional rigidity of the.
Oh, you
Yes,
mean
yes.
with that oscillation, you will get the rigidity of the
Yes.
also, right? That's probably what you are hinting at.
With the same system, one can do that job also.
Okay, okay, yeah, that's correct. If you have something, then you'll have to have one more measurements probably to get the rigidity, or is it then? I don't know. I mean, if you have a metallic wear, then its rigidity. So the return force is coming from the rigidity as well as Earth's magnetic field. So how will you disentangle those two? I don't understand. Maybe you have to make a third measurement. Maybe we can discuss it later on. I mean, how the work can be extended. But this is, I think, a very simple deflection magnetometer using only a magnetic needle. Only thing, I mean, you'll have to place I mean, the line on which Makun has drawn two perpendicular lines. On one line, he has put the magnetic needle. The point that should be mentioned to the students is then he'll have to rotate the paper on which the needle has been placed so that one line and
Yes,
the
sir.
magnetic needle come in one plane so that you know that line is along the north-south Earth's magnetic field. Then on the perpendicular line, you place the marble. So that will be pointed out to the students. Okay, so I think Akun has been meaning. Shall we go to the second?
Pa- Participants, please mute yourself. Some noise is coming. Yes, thank you. Yep. Sir, whether Dr. Goswami he will continue or
No, I think as the I mean,
as plan, yeah.
yeah,
Perfect.
let
Okay.
him have some rest and then he can
Yeah,
continue.
I think okay.
Yeah.
Okay. So
Okay.
thank you, sir. Thank you, Dr. Goswami, for demonstrating these interesting experiments. And now for the next technical session, I request Dr. Shurajit Chakraborty, sir, to give his presentation. He will explain how we can measure velocity of sound by using some simple devices.
এটা
Sir,
হয়ে গেল।
over to you.
কি হলো?
Okay. So can everyone see my title page?
Yes,
Determination.
sir. Yeah, yes, sir.
Okay. So this is a very old experiment. I mean, determination of the velocity of sound by resonance air column method. I think this experiment is not done nowadays. Maybe in the past course it is there. It is very simple. By doing this experiment from your room, from your home, you can determine the velocity of sound. So let me show you. Okay, so first the introduction is a very old one, and as I've already stated that this experiment was designed only to give students an opportunity to get the velocity of sound from home. Okay, so let me give you the setup figure, the photograph of the setup. So what is there? I have a 250 milliliter semi transparent cylinder, measuring cylinder. What I have done, I have punched a hole at the bottom of this cylinder. Now, if you put water up to a certain height, then if you open this hole, then the water will come out and water level will fall in the cylinder. So initially, you'll have to keep the hole covered by a sellotape, fill it up to say top height of this. I will show you some videos later on. So this air above the column of water is the air column which will resonate at the given length. The sound that I will be using is through a mobile phone. Once again, you can see mobile phone serves you as a source of sound also. Now there are hundreds of source of sound available on net, but what I use is through FeeFox software. There is a very good software called FeeFox. It has been developed in the Aachen University of Germany, and Madam Shinjini will give you the name of this software in chat box. So
Yeah, it's already given. Yeah, they
okay,
can get it from
so
chat box.
you can have a look at the name of the software. It is very easy to download it from Google Play Store. Once you download it, then you can use this software for several reasons. For example, in the first portion of this software, you will see they are using several sensors of your mobile phone and give you how to use that and get several measurements. So once you download it and set it up on your mobile, you can just play around with this software and come to know several physics experiments that you can do with your mobile phone. In the first section, they give several sensor description and how to use them using the sensors in your mobile phone. In the next section, they give you some experiments that you can do on acoustics. In that section, the last subsection is called a tone generator. It is very simple. You switch on this tone generator, and you can, if you run this, in the very beginning, it will start giving you a sound of 440 hertz. There are, I mean, you can change this frequency to whatever frequency that you need, and run the FeeFox software, and you'll get the sound. So I downloaded this software FeeFox, and I have set it up in such a way, but for this I had to use a stand. So this will be the main hurdle for you to set up this experiment at home. I have a home lab sufficiently with sufficient ingredients and components, material. So I have a stand also, so I didn't have any problem. So if you can use your imagination or ingenuity to think how you can place your speaker of the phone right on top of this cylinder. For example, one solution could be piling up certain thick books, say dictionary or some encyclopedia, 6, 7 of that you can put one upon another. The height of this 250 milliliter cylinder is about 1 foot. So maybe 6, 7 books, if you pile up one after another, then you can put the mobile phone, say 1/4 of it sticking out, and the speaker is on that part, and the rest 3/4 is on the pile of books. And you'll have to, for the safety of your mobile phone, maybe you'll have to put certain 1 or 2, 3 books on top of this part which is lying on the pile of books. So if a little part of this mobile phone sticks out with the speaker, then you are through, you are done. You set up the FFOX software, bring it to the tone generator mode, and you can choose your frequency. That is also there in the FFOX software. So you choose your frequency. I chose 2 kilohertz. That is 2000 hertz I chose, and I did this experiment. The idea is, if you have the source running at 2 kilohertz, then you open the sellotape from here, water will start, I mean, going out, and the water level will come down. And when the resonance occurs, that means the first resonance will occur at lambda by 4. You know, this is a resonance column with resonating lengths at lambda by 4, 3 lambda by 4, and 5 lambda 4, like that. So on the surface of water, it is node. There is no vibration. You have to remember, sound is a longitudinal wave. So the waves that are coming out from the mobile are longitudinally oscillating, but at the surface of this water, it is a node, and other points are antinodes. The first antinode will be at lambda by 4. That means the length of the air column, when it is equal to lambda by 4 of the wavelength of sound, then it will start giving resonance and the sound will appear very loud. So initially what you have to do, set the sound level to very low, just audible level, and then you start, you remove the sellotape from here, water will start coming out, water level will go down, and as soon as there is resonance, you will see that the sound is very loud, and you can very easily figure it out that it has reached the resonance period, resonance condition. Now, finding the exact position may be difficult. So what I suggest, you can very easily take a video of this process by another mobile. So this mobile is already engaged. So you may have to borrow another mobile from your father or mother, and then you can take the video of this process. I will show you the video that I have taken in the next few minutes. And from that, you can run that video time and again to find out exactly at what position the resonance is occurring. So now let me show you some videos. Okay, so maybe this is hide. And then just a moment. Yeah. So this is the first video. Is it visible? The figure, is it visible?
Yes, yes, sir.
Okay, so now let me run the video. So what I have done is, this is the cell phone is on top. I mean, you can see there's the speaker is also there in the middle of this. It does not come in this picture. So I have stuck a paper with its 0 at the top of the cylinder. So from there to this point is 1 centimeter, and I am happy with this. I mean, discount of 5 millimeter. I mean, one can't measure the resonance position to better accuracy than that. You will soon find out. So I have just marked them with pen. Otherwise, the video doesn't come very well. If you have the marks on there are marks on the cylinder itself, but if you take a video, that doesn't come very well. So I have marked them with black ink, and now if I run the video, you'll see how the resonance shows up. You can very easily see that some resonance has occurred around 2.5. So maybe at one shot, you may not find the exact position of the resonance. The advantage of video is, you have taken this video and you can run it 100 times. There's no problem. And then you can find the exact location. So it appeared to me that it is around 2.5 centimeter from top. So, okay, so let us run it once again. Now let's see. It's 1.5 centimeter. Water level, you can see it is coming down. Maybe between 2 to 2.5 centimeters. So you'll have to take a number of readings and take an average. That's all. So you have the first position of resonance, that is a lambda by 4 from top, the water surface here will be the node, and antinode will be somewhere here, that I'll come to later on. It is slightly outside the top of this cylinder, that I'll come to later on. So this is at the 1 lambda by 4. Now let me show you the another resonance that is around 10. So let me run this. So it looks like it is around 11 centimeter. This is clear. The resonance is occurring. It is coming to a maximum and then it's going down. So it is very clearly, I mean, recognizable. I could get another resonance. Let me see. That is around 19 centimeters. So let me run, and it's. I will take it up to about 12. So 19. This is audible. Then there will be around 19.5. So you could clearly make out that there has been a resonance around 19.5. By looking at this video a number of times, you can probably get a better estimate of this resonance position. Now you have 3 positions of resonance, lambda 1, lambda 2, lambda 3, that I will show here in my presentation. So I had the frequency of 2 kilohertz. Okay, so what was the necessity of taking this high frequency? That is because I wanted 3 resonance positions, so that the maximum will be 5 lambda by 4. So I mean that has to be accommodated within this 1 foot of the cylinder. So obviously the wavelength has to be rather small. So I have to have a large frequency of about 2 kilohertz. So first resonance was obtained between 2 to 2.25 centimeter. I take the average position as 2.12 centimeter from top. Similarly, second resonance is at 10.75. Third is at 19.62. So from that, I get R1 minus R2 minus R1 will be lambda by 2. So one is at 3 lambda by 4, another is lambda by 4. So you take the difference, that will be lambda by 2. Similarly, R3 minus R2, that will be once again lambda by 2. From that, I get the actual lambda. And from third to 1, that I get it will be lambda. So that will be 17.5. The average comes to about 17.5 centimeter. So you see, using a 2 kilohertz source, I am getting the average wavelength of sound of 17.5 centimeter. Okay, so from that I can calculate the velocity of sound, and it's very simple. V is equal to n lambda. So lambda is 17.5, n is equal to 2 kilohertz. So the velocity turns out to be 350 meters per second. Room temperature on that day was about 29 degrees Celsius, and you know how to calculate the velocity of sound at a given temperature, knowing the velocity of sound at 0 degrees Celsius, and the formula that is available in every book. So using that formula, that is the velocity dependence of velocity of sound on temperature, you can calculate the velocity of sound for the day on which you are doing this experiment. So you'll have to somehow measure the temperature of the day. So from that you can calculate. So you can see how beautiful result I have got using this simple arrangement. So the main part of this experiment, the difficult part, is setting up of the mobile phone if you don't have a stand. And more difficult point is how to drill a hole at the bottom of this. This is most difficult part. I don't suggest that you do it right now, but because you are doing experiments for the first time. Maybe you can seek some expert help. Maybe the vendor who is supplying you this cylinder, you can ask him to drill, not exactly drilling. There are some other things by which you can do this. About a 1 millimeter diameter hole. that has to be punctured at the bottom of the cylinder. That is a more difficult task. I do it all by myself, and that for that I need rather thick needles, okay, of 1 millimeter diameter, that are available with cobblers. You have seen probably, I mean, they mend your shoes with these needles, rather thick and long needles. They are available in the Chandni market. So if you are, someone of you is enthusiast, can easily get that needle from Chandni Chowk and drill this hole yourself. But I mean, that will require, I mean, little more enthusiasm. And for that, I just heat it up a little bit, and this press against this surface of this cylinder. It will make a hole and it will go in. But then taking it out is more difficult job. That needs an expertise. You see, I mean, if you allow the hot needle to cool down, the melted part of this plastic will grip on this needle, so it will not be easy to take it out. So it needs some expertise. I mean, what I do is, when it has cooled down a little bit, so the plastic, molten plastic, has once again solidified, I put some 2 pieces of ice on the needle, so it differentially cools more than the plastic, molten plastic, and then I can easily take it out. So this is a trick. I mean, you may not, attain expertise for doing this in the very beginning. So I won't suggest it to you right now. So maybe you can take the help of vendors to drill a hole of about 1 millimeter diameter at the bottom of the cylinder. So that way you can do this experiment very easily to find the sound velocity at your room temperature, sitting from your home. Now, I mean, once you have done this, I mean, you can find the position of the antinode that is on top of the cylinder. So if you know the lambda, if you have lambda, for example, you have found the lambda as 17.5 centimeter. So you know, for example, lambda by 4, you know what is that value. And you know the resonance position, that is about 2.5 or something. So you take lambda by 4 from that point, and you will see that is going beyond the top of the cylinder. So actual node is being formed outside the cylinder. That is a very clear observation. Maybe last 150 years people have observed that, and there is a reason, very deep reasons for that. I'm not going into that. Actually, Julian Schwinger has a paper in 1950, more than 100 years back. No, sorry, 1950, 70 years back. So he deduced a relation to give that this position of the antinode will be outside the cylinder by a length of about 0.6 r, where r is the radius of the cylinder. Now, when I calculate this, I get a different value, about 0.9 r. But I am getting the value of the sound very good. So I cannot say that my finding is wrong. What is happening is, at that old times in 1950s, people used to do this experiment with heavy tuning forks, and with that, frequency of about 500 hertz or 600 hertz was difficult. People used to do it very low frequencies of 200 to 300 hertz, and for that the wavelength is very large, you can easily calculate. So the ratio of the diameter of the cylinder to the wavelength of sound was very small. Here my circular diameter of the cylinder is about 4.5 centimeter, but wavelength is only 17. But in those days, people are using 5 centimeter, 6 centimeter diameter cylinder with a wavelength about 100 centimeters. So this was about 4%. But here my 4.5 centimeter is the diameter of the cylinder, as against a height of 1 foot. And that comes to about some 33, 34%. So in Schwinger's calculation of 0.6 r, this was, I mean, taken as granted that the ratio of the cylinder diameter to wavelength will be very, very small. But in our case, it is not like that. So I don't I mean, I don't think that 0.9 r as a end correction that I am getting is wrong. It is okay since the velocity of sound has come correctly. Okay, so now, okay, thank you all for your kind attention. I have come to the end of this talk. Maybe now I hand it over to Dr. Dashgupta. Shinjini.
Yes, students, if you have any question, you can post it on the chat box. But at this moment, I cannot see any question in the chat box or Google Meet. No, not in YouTube. But you can download that Firefox, that free app from Play Store, and then you will actually learn, or you will get an idea that how you can use your mobile phone, which is like a lifeline to you for the physics experiments. So that will be a fun for you and also an like new invention. So I thank sir for delivering this. I mean, very interesting idea. So thank you, sir.
Okay. Thank
And
you.
now we move to the third part of our technical session. So Dr. Makhonlal Nando Goswami sir will now demonstrate some electrical experiments which can be done easily at home. Sir, the stage is all yours.
Okay.
Shurjit sir, you have to stop
Yes,
presenting. Yeah.
yes, yes. I've
Thank
done.
you.
Present now.
Yes, sir.
Is it visible?
Yes, sir.
So
So just one thing, if you go to full screen mode, I think then it will be a
more
bigger
clear.
one. Yes, full screen mode.
Yes, yes.
Yes, sir. It's better now. Thank you, sir.
So next experiment is measurement of unknown resistance by the Western bridge principle using 100 ohm potentiometer. Uh, Actually, unknown resistance can be measured by meter bridge. In our laboratory, in the physics laboratory, the meter bridge is basically the modification of Wheatstone bridge network used to determine the value of unknown resistance. So Wheatstone bridge is one of the most common, accurate and reliable method for the measurement of unknown. And its principle of operation is based on the null deflection. But the meter bridge consists of a thin, uniform conducting homogeneous conducting wire in a placed in a rectangular wooden board, and there are number of gaps. That means for unknown resistance, by metal strips, and unknown resistance box, jockey, galvanometer, rheostat, etc. involved in the meter bridge. But here, actually using this principle of Wheatstone bridge, when the galvanometer current is 0, at the null point, null deflection, that the principle is very simple. If this P is a resistance, Q is a resistance, and R and S resistance, if S is unknown, then we can measure by using this relation P by Q is equal to R by S. Now, in our experiment, we have performed this actually meter bridge experiment. We should say the meter bridge experiment, but in the other way, we use a potentiometer. Potentiometer, all of you know that potentiometer is basically a three-terminal resistance with three terminals. Generally, there are three terminals, and the middle terminal is used for the floating point. But in multi-term potentiometer, usually called pot, this is just this multi-turn pot, 10-turn pot, 100 ohm. And we use a digital multimeter. We use resistances, carbon resistance, and a breadboard. Breadboard is basically used for the one by one. This multimeter used for the current measuring, or we should say replacing this galvanometer. We can use multimeter, and the breadboard. Before the breadboard, we used that hero board. After breadboard coming, it is very easy to connect the circuit, and breadboard is connected in that way that there are two strips, and 5 points in the middle, and these every 5 points are connected, and the vertically, and the horizontal to strip upside and downside. There also the 5 points are connected up to the middle in that way. So circuit connection is very easy. Without soldering, we can make the circuit by putting the wire in this connection points. So components required for the measurement of unknown resistance: a power supply, and ordinary power supply in the market is 300 400 rupees its cost, but the mobile charger is only 50 rupees, and mobile charger can give the supply. Resistances 100 ohm, 47 ohm, one breadboard. This carbon resistance has no such cost. Breadboard is around 80 rupees, and one digital multimeter. This is also around 100 and 120 rupees. And that 100 ohm pot, 10 tons, this is around 200. So using these components, we can measure the unknown resistance. Very simple circuit. Circuit is here the mobile charger, and we can put around 6 volt here. This is the one arm AB, P is here, and BC, Q is here. This is actually from A to C, we can put a 100 ohm pot of 10 tons. Before going to this 100 ohm pot 10 tons, its action, we should calibrate this 100 ohm pot. How we can calibrate this 100 ohm pot? This pot has 10 tons, and when the minimum position means the floating point is in minimum is in 0. That means one end and floating point is same. This is the minimum position. We can put a mark there. If it is this spot is bluish, so we can put white mark, and we can put this mark here up to this pointer. Pointer means this variable part. So this is actually 0, and just opposite to that part we can put one mark, and within this, that 0 and opposite part, we can put 4 different not as different, 4 mark evenly, means we can get the from 0 to 5, and also in the opposite direction we can put 4 evenly distributed marks, and we'll get the 10 division in this pot. 10 turns, and we will get the 10 division for 100 ohm pot. So every mark or every point can give us 1 ohm resistance. So this is a very fine tuning for the variation of resistance in the potentiometer. And here, that if the variation of ohm, if we calculate the number of turns and this point from 0 to from here, if we calculate, then we can easily calculate the resistance of one side, the resistance of one side. So this circuit can give the resistance from A to D, if A to D is R and D to C is 100 minus R. That means that P, R and S, which would say S, that is 100 minus R, you know. So we can put here the DMM when the DMM current is 0 after connecting this circuit. DMM current is 0, that means bridge is balanced. Then we can measure the value of Q. So this Q value, that means expressed as Rx, unknown resistance. So P is 100 ohm. We have used this breadboard and carbon resistance, connected this circuit, and using the null deflection. And here not as a deflection, basically the current in DMM is 0 by varying the pot, and we will get the value of unknown resistance Rx. Initially we have put 100 to check the pot resistance and variation of the variable resistance. P100, Q100 will get when P100 ohm and Q100 ohm, then DMA is connected to the middle point, narrow middle point of the variable resistance. That means complete 5 turns have been done. If we completed the 5 turns, then only the bridge is balanced. So we have used 100 ohm pot for null adjustment between B and D. Now we replace the 100 ohm in 100 ohm of that QR and put the unknown resistance Rx. We have put 47 ohm and measure the resistance of one side of the pot. We can calculate the unknown resistance by using this formula. Rx is equal to this, as P is equal to 100 ohm. And interestingly, we have got the result that when 100 ohm in P and Rx is 47 ohm, you can got the R 68 and R is 32. Actually, you can measure 68 ohm first, and 100 minus R is 32, and you will get the 47.1. Sir suggested me you can series 247 ohm resistance, carbon resistance. We have also performed this, and we'll get the 94.1 in this precious result, in this precise result, that way. So unknown resistance can be measured very easily using the 10 turns 100 ohm point. I can emphasize for using this 10 turns 100 ohm. But it can be used to study the measure unknown EMF. It can be used to study the thermocouple EMF of thermocouple measurement. So it is very useful pot for the study of for the measurement or for the determination of unknown resistance. And also the second part of this
Makhon, Dr.
sir.
Goswami, can
Sir.
I make some comment at this point?
Sure, sure.
Okay, so you please go back to the circuit diagram. Now, yes, this one. Let me try to explain the pot little more in detail. I think that is the most crucial point. Our aim was to replace the bulky meter bridges or potentiometers by this very little, about 5 centimeter diameter contraption. This is called a potentiometer in general, but more commonly it is known as a pot. So we have chosen a 100 ohm 10 turn pots. Now I should explain this 10 turn business. Now you see from A to C,
Yes.
it is 100 ohms, right? Now there is a pointer which can be rotated by the handle of this pot, and if you rotate it full 10 times, then the a floating point will come from one end A to C. It will traverse a 100 ohm resistance. That means in one full turn we are coming to 10
10
ohm.
ohm.
Okay, so in one full turn we coming to 10, and that Dr. Goswami has calibrated in 10 equal parts. So you can realize that we are, I mean, with this instrument we are getting a least count of 1 ohm. This is very good. That's why I chose this 100 turns 100 ohms 10 turns pot. So there you can make a measurement of great accuracy, but in the cost of only 185 or 200 rupees, whereas a big potentiometer with 10 turns of the wear, that we can cost you at least 5,000, 3,000, 4,000 rupees. So it is a very simple arrangement with which you can measure resistance with 1 ohm. I mean, that is your least count. In each full turn, you are traversing 10 ohms, and he has calibrated it in 10 equal parts, so each part is 1 ohm. So if you
Yes.
turn it 5 times or 6 times, suppose you turn it 6 full times, and then the pointer is pointing at eighth mark. So it will be
Yes, for 68.
six turns means 60, and then 8 mark 668. So
68.
you are getting these resistances to an accuracy of 1 ohm, which is very good. And he has done it with eye approximation. It is probably his mark was in between two marks. So he has taken it as 0.5. So
1
by,
and 2.
sorry,
Complete complete 5 turn, and then between 1 and 2. That's
So
why
it
I
is
am
1 ohm and then 0.5 he has taken.
right.
So it
Right.
has 51.5. So
Right.
it is the beauty of this instrument. Since it is 10 turn pot, I mean, your sensitivity goes very high. You can actually measure with a 0.5 ohm accuracy. So this is not easily achievable with so expensive a potentiometer. It's useless. I don't know why. I mean, universities always suggest this huge instruments, and this is easily available nowadays. 10 turn pot, even 100 turn pots are also available. This is cheaper. If you go to higher turns, then that becomes very expensive. This is within our range, about 200 rupees, nothing. So with that, you can see, I mean, you can go to a very high accuracy, and he is getting some beautiful results. I mean, normally it is given on the color code, it is 47 on, and he's getting 47.1, and he has used two resistances in series, and he is getting it 94.1. So this is, I think, a very interesting replacement for normal meter bridge. Okay, Makun, you can go ahead.
Next, I have measured that the measurement of unknown EMF of a source by null adjusting method using 100 ohm pot, and this is also 10. Very simple. It's theory of working formula. If we put a standard EMF and RS is found such that if IDMM will 0, that means this is also a null deflection system, or we should say the zero current through the digital multimeter meter. Then this is the relation which first we have to figure out. This is the circuit diagram. So this is 6 volt power supply, and current will goes through that way, and this is a variable power supply or variable source. This variable source is used for standard EMF and for unknown EMF. When there is no connection between the standard EMF and the circuit here, that RS means this pot, then the current goes through that way. This is I. So if we put the standard EMF, yes, here, then ES equals to actually I into RS. And in the similar manner, if we put another source here, then current goes through that way, that EX is equal to I into RS. So from this measurement, we can determine the EX, that means unknown EMF, from the measuring the RX and RS, and the measurement of RX and RS can be done by this pot. if it is RS and it is RX, and from the port, that 100 ohm port, 10 tons, we measured this RX and RS, and comparing this RS and RX, we can immediately determine the unknown EMF. This is another experiment. But sir asked me to keep the mobile charger, to avoid the mobile charger for fixed 6 volt 6 volt 6 volt EMF, 6 volt source here. If it is if we put the mobile charger, surely voltage drop, but up to 3 volt it is not, sir. I found it is around 5.6 or something like this. So we have to study more with variable supply. I have taken one supply with 1.54 EMF voltage, and one is 3.17 voltage. So this is actually two standard sources, 1.54 and 3.17. So if we put mobile charger, what will be the actual effect? I have not studied that way. But the value of that RS and RX can give the value of that unknown EMF, if we know the value of standard EMF. So this is also one important thing, is that 100 ohm port of 10 tons, very smooth, and we can use for the measurement of unknown EMF. So this is the main idea, to study the EMF or measurement the unknown EMF using null adjusting of that potentiometer, 100 ohm, 10 tons. Sir, any comments?
Makun, have you finished?
Yes, sir.
Sir, one question.
Yeah. There is a question, so if we answer that.
One question from Narayan Ghosh.
Yes,
That
yes.
can you use DMM to measure resistance of both sides of pot? Can we use DMM, digital multimeter, to measure resistance of both sides of pot?
Yes, yes. We can measure the resistance of both sides of the pot, but then we have to put the we have to, if we have one DMM, if we have more DMM, we can use that way, and breaking the circuit, we can use both side of the we can measure the both side of the pot, resistance of the both side of the pot.
Makun, can I make a comment here?
Yes, sir.
Okay, so first of all, students have to understand that can you show the other diagram that you had shown in the determination of unknown resistance, the first figure? Yeah, the figure, the diagram, PQ and all these things were there.
Yes.
That one, the first circuit that you had shown. Yeah, this one. Okay, so now A to C is the full 100 ohm, and that part has been shown in the small part. Okay, so it has three terminals. One terminal at this point, one terminal at this point, one point is there. But as you rotate the uh, I mean this the spindle to rotate it 10 times, that actually moves the pointer from this end to that end. Okay, so you have three contact points. If you put a digital multimeter between this point and this point, it will give you the resistance of this part. And keeping this point fixed, if you take the other terminal of the digital multimeter at this point, then you measure this resistance of these two parts. If you add up these two resistances, then it will give you 100 ohm. Maybe there may be some error of 1 or 0.10. I don't know that. So you can easily the question.
No, actually, sir, 5%
Okay.
tolerance is there.
Okay, so 5%.
Actually, 100 in place of 100, it will give you
5 ohms. Okay.
102 ohm, 102.3 ohm. I have found.
Okay, so the answer to the question of Deep Narayan, you can measure the resistance of both these parts. Your central part, when you rotate the spindle, it moves along this direction. So one end, when you put at this end, it will show you 0 in principle. And as he is saying, about 5% tolerance is there. So it may be within 2-3 ohms difference maybe. So when you put the spindle on the leftmost part, by rotating it, you come to the minimum point. It is actually in principle, I mean, coincident with this point, so it will give 0. So resistance between this point, actually this point and this point itself. Then if you rotate it 10 times, the floating point is actually moving around and coming to this point. When you finish 10 turns, you have moved along from this point to this point by 100 ohms. So if you are at the middle point, then this part of the resistance, that means if you connect your DMM to this point and this point, it is Rx, and one floating point keeping fixed. If you move this point from here to here, you are getting 100 minus Rx. You can measure both these resistances with DMM, so no problem. Okay, so now let me
one point, Dr. Chakraborty. One point. Makhon sometimes told that he measured thermo EMF.
Yeah. That is a different. That can also be done probably. Yes, so that he will be doing later on. He has not yet tried. That can also be done. I mean, only thing you will have to, in the main circuit, you will have to get a very small current of the
small in fact, small source.
Microampere region.
Microampere range, and the EMF, the source EMF should be very small also.
Or you can add a mega ohm resistance in that circuit.
Yes.
That you will try later on, because you will have to measure microvolt range of resistance. I mean, the EMFs.
I want to give a project for this.
Okay, very good. Okay.
Because there is a potentiometer of huge, the 10 meters length of that.
Okay, so now let me try to explain. Makhon, can you go to the potentiometer circuit?
Yes, sir.
Yeah, keep it there. So since these students are only first year, second year, probably they have not seen a potentiometer in the lab, or they don't know the principle of this, first of all. So let me very briefly tell you the principle of a potentiometer. Now you see this point is shown here with an arrowhead. Okay, so that means it can be moved along this thing. So if you disconnect it, that means you remove this point from here, which he has shown in the second figure. Yeah, he has removed this. It means this point of this cell is not connected to this resistor. So what is happening now? This is 100 ohm. This is the pot.
This is 100 ohm.
Yeah, so this is 100 ohm and 6 volt is connected. So a full current of I is flowing, that is 60 milliamps. 6 volt by 100 ohm that is
Right.
60 milliamp. Okay, so now when he connects this, then I mean, when it is not a null condition, that means you go to the earlier circuit diagram, Makun. No, not this one. In the potentiometer is this one. So when this DMM is connected at this point, then there are two branches. The current can go through this as well as from this. But when it is in null condition means in the DMM shows voltage 0, or if it is in current mode, it
Current zero.
shows zero current. You have used it in current mode, right?
Yes, sir. Yes, sir.
Okay. So students must be told that this DMM can be used to measure voltage as well as current, but their modes are different. You'll have to turn the knob of the digital multimeter to change it from voltage mode to current mode. Dr. Makhan Pal has used this in the current mode. So when by moving the arrowhead of this of this potentiometer, that means by turning the spindle of the pot, you are moving this to this end. At certain point, there will be, there will be no current through the digital multimeter. That's what is called null condition. Under which condition this will come? Okay, so when this is null condition, this is once again 6 volt is passing through this 100 ohm. So I is equal to 60 milliampere. Now 60 milliampere going through Rx, suppose that is 30 ohm or whatever, 3 turns has been produced. So 30 ohm into current, that gives the voltage. Okay, so if that is the null condition, then what it means, this cell, because of higher potential at this point and lower potential at this point, is trying to send the current through this cell in its opposite direction. This cell will try to send current in its natural direction this way, clockwise. But if this point is high voltage and this point is low voltage at a 30 ohm, then 60 milliampere into 30 ohm, that voltage, if this can balance this voltage, then only there will be, because this voltage is trying to send the current in the anti-clockwise direction, whereas this cell, this is the fixed cell that he has used for the first one, that this is a variable, it's unknown. So this is trying to send current in the clockwise direction. So
Yes.
null condition will come only when these two potentials, that is the EMF of the cell, is equal to the voltage drop across this small part of resistance Rs. This is the beauty of this potentiometer principle. This is the basic principle of a potentiometer. You balance the, so you can very easily understand that in order to get a successful result, the voltage of this cell, which is basically driving the current, that has to be greater than whatever voltage of this cell. This is a point that Dr. Makon had missed. I mean, in order to be successful, this voltage has to be larger than this. If it is 6 volt and you apply a 8 volt, you will never get a balance here. Okay, so this has to be less. By finding RS, you can find the voltage of this. I mean, you get to know the voltage of this one. It will come to the same thing. So now you using a different voltage, because if it's a variable source, you can put this voltage to a different voltage, and use this to find the Rx here and ROI here. So taking the ratio of this and this, you can get the unknown voltage of this one. With this voltage, which is, you find out the distance, that means Rx, which balance this thing.
Yes.
Using that, you can find an unknown voltage. So this is the principle of potential. First, you have to understand the principle of potentiometer, how it balances, and the null condition, you have current only through this part of the circuit. So you know what is I. He is using I, though we are not using it, we are getting a cancellation from numerator and denominator, but this is 60 milliampere. So I hope this makes things clear.
If I'm permitted to interrupt,
No,
Shubhadip,
no, no introduction, Chinmay. You can go ahead.
no, that's why I think you will be able to explain it better. That's why perhaps potentiometer is called potential divider, and
Yes,
you are
yes,
very
Yes,
emphatic
sir.
about saying that the voltage should have been less than 6 volt,
yes,
because that particular point is connected in opposition. That is
yes, in opposition. That's
in
one is
opposition.
sending, one is trying to send clockwise, other is anti-clockwise.
Right, right.
So when
So
these two are
that,
same, then only one gets the null condition.
that's why one name of the potentiometer is potential divider,
Ah, yes, yes.
which is also, I think, served by a rheostat. Rheostat can
Yes,
also
yes,
be
yes.
used as a
But
potential divider.
rheostat is not so beautiful in the sense this 10 turn pod is so sensitive. I mean, you will love to work with it. I have worked with it. I fell in love with this thing. It's so sensitive. You very smoothly you can change the voltages. Beautiful 10 turn pods.
And not only that, my sensitivity from the point of view of getting a deflection at the galvanometer when it is away from the null point. That is more
Yes,
important.
yes. And nowadays we are always using, I mean, in our experience, digital media, but because we don't want galvanometers and things like that, these are not easy to manage at home. In our main
Digital
purpose,
multimeter, sir, digital multimeter can give the zero current and in the microampere range.
Right, right,
yes, yes,
right.
yes,
So
exactly.
highly sensitive.
Yes,
Right.
very sensitive. So that's the purpose. I mean, it gives the null condition, and that can be checked by digital multimeters. Okay, so Makon, do you have anything more to say, or you have finished?
No, sir. This is
You have finished, right?
is
I don't see much comment or questions in the chat box also. Shinjini?
Yes, thank you, sir, for your detailed presentation, and also I thank Dr. Chakraborty for giving us the basics of the potentiometer and also this beautiful idea of using this 10 pot turn, this 10 turn pot instead of using a huge potentiometer that we usually do in our practical labs. So
yes.
at least we are getting some idea that how even using very simple things, very small, and maybe also cost wise effective things, we can do the experiments which usually done in a very cumbersome way. So thank you for giving us this beautiful idea. So hopefully the students can try it. Maybe they will need some support from their college to perform these experiments because they need the variable source, also the digital multimeters, but at least they can try it. Okay, so thank you, Dr. Goshami, for your nice presentation. So
Okay,
shall
thank
we
you,
move
ma'am.
to the next part, or
Yeah, I think though, I mean, I don't know whether Deep Narayan is there. Is Deep Narayan, you are there?
Yes, sir. Yes, sir.
So are you ready? Can you, though yours was scheduled on second, can you say something? Because you still
Okay.
have
Okay.
some time.
Yes, sir. Yes, sir. I am ready.
Okay, so Shinjini, you can introduce Narayan. He is ready with his
yeah,
experiment
sure.
that was supposed
Okay.
to be delivered on second of
Third
December.
Mr.
Since we have
Okay.
some time, we can go ahead till
Yes.
maybe 6 o'clock.
Okay.
Okay.
Okay. Okay. So all other participants, please mute yourself because noise is coming from somebody. Dr. Goshami, please stop presenting.
Yes,
So
yes.
now,
1 minute.
now we will move to the last technical session of today. So, and this session, our resource person is Deep Narayan Ghosh. He is the assistant teacher of physics, Vidyasagar Shishu Niketan, Medinipur. He is interested in project work and designing new experiments in physics. So, welcome you, sir, to deliver your lecture. And he will be elaborating very useful home experiments with thermistor.
Thank you, ma'am. Welcome to everyone. So I am today going to show, and under the guidance of Honorable Sir Dr. Subhash Samanto and Dr. Surajit Sir. So I am going to show a simple experiment using thermistor, how to use thermistor as a thermometer. And it is basically most sensitive thermometer also. I am going to show you. Can I share my screen?
Yes, sir.
Okay. Sir, is it visible my screen, ma'am?
Yeah, it's visible,
Okay.
sir.
So my project is calibrate thermistor as a temperature sensor. That means like as a thermometer. And also I have verified the Newton's law of cooling with this project. So thermistor basically a device with two terminal. It is mainly used for temperature sensor and the combination of thermal and resistor. Thermistor is a combination of thermal and resistor. It is mostly made of some semiconductor, sensitive semiconductor like some metal oxide or maybe use silicon oxide or other. So this thermometer is used basically in our sensitive device like our lithium in protection device, say our laptop battery or our mobile battery. In this mobile battery temperature sensor or laptop battery temperature sensor, the thermistor is basically used, and many more in many more devices the thermistor can be used. So next is type of thermistor. There is two type thermistor in available. One is PTC. PTC means the positive temperature coefficient. That means if we increase temperature, its resistance will increase. If I simply draw a graph along temperature theta versus resistance R, in case of PTC, the curve will be like that. With increasing theta, resistance increased. Some metal has also property that type, but in NTC thermometer means negative temperature coefficient. Its curve will be different, and if we draw resistance versus theta, its curve will be like that. So if we measure resistance and we calibrate the thermistor so that for particular resistance it will show a particular uh, temperature, then after calibration we can be use the thermistor as a temperature sensor. Or okay, it can be used as a temperature sensor. So next is thermistor characteristics. So its characteristics governing equation is like that: R equals to R reference e to the power beta into 1 by T minus 1 by T reference. So T reference, maybe I can take in a normal room temperature, and R reference is the resistance at room temperature, and R is the resistance at temperature T Kelvin. So if I simple calculate from this equation, I can get ln R equals to logarithm of R equals to beta by T plus ln R reference minus beta by T reference. So you can see that the ln R logarithm of R is proportional to 1 by T. That means it will form a straight line curve. My next is, so if we draw a graph, this graph will be just like that, 180 versus LNR graph. So to verify the Newton's law of cooling, we know that according to Newton's law of cooling, the rate of cooling is proportional to the temperature difference between surrounding and substance. So here d theta by dt means here theta is taken as temperature, so and t is taken as time. So d theta by dt is equals to c into theta minus theta naught. Theta naught is the surrounding temperature and theta is the temperature which is taken in Celsius scale. So and here c is a constant term. Also its c depends on mass and specific heat capacity of substance. So if we take a constant amount of substance, then C is constant, and its specific heat capacity also constant. And integrating this equation, that d theta by theta minus theta naught equals to C into dt, I can get um, again logarithm function of theta minus theta naught equals to ct plus c dot c dash. C dash is another constant, and as I have integrated, there is no limitation of integration, so there is another constant c dash. And again, sorry, again, the logarithm function of theta minus theta naught is proportional to the time, and it will also show the straight line curve. I will show. So our experimental setup is very easy. We have to use one DMM, means digital multimeter. We know by a single digital multimeter, we can perform several number of experiments. So this is most useful element for our experiment. And one thermistor.
Just
Thermistor is
one interruption. Just one interruption, Mr. Ghosh. The
yes,
last
sir.
mathematical step should have been better explained. That your C prime gets absorbed in e to the power of C prime, which is the constant multiplier, and that's why your ln theta minus theta naught becomes proportional to C. We can understand, but for the benefit of the students, I think you could have better
Okay, sir.
explained the last step. Okay, it's up to you.
Okay, okay. Sir, I am going to explain. The left hand side, we can get ln theta minus theta naught, and in right hand side it is ct plus uh,
And also ln of mod of theta minus theta naught, though here that is not required, theta will be more than theta naught, so that is fine. But ideally, you should say that ln of mod theta minus theta naught when you perform the integration.
Dr. Ghosh, I mean, what he will do later on is he will plot log of theta minus theta 0. Theta 0 is the room temperature. He will come from higher temperature towards room temperature, and that he will plot as a function of t. Then the slope will give you the c, and intercept will give you the c prime. That's, I think, his idea was for this equation.
yes, sir, and also
And
theta
that's
greater than theta
exactly
naught.
No, that I can anticipate. So his C prime has got lost in his explanation. C prime
so
has
he
got
should have
lost.
told that in the plot that can be obtained from the intercept. That's all. Otherwise, as you are saying, this is very correct. You can say C prime as something, some log theta dash or something. You can get
Okay, okay, yes, sir.
absorb this in this thing. Yeah. So he will put this equation. I think he has shown me some graphs. So there will be some intercept. That's all.
Thank
Okay.
you, sir.
Okay.
So in our experimental setup, we need some multimeter and we need a thermistor. It is very cheap. We can get at the price of 2 to 5 rupees. And to verify Newton's law of cooling, we need a stopwatch. We all know we have a mobile phone. It has most sensitive. It is the most sensitive stopwatch also. And we need some hot water. To get hot water in our home also, we have gas or stove. By this we can heat the water, and we need also a thermometer also. We have to buy a thermometer only, and a multimeter. So the circuit diagram is very simple. We are as the multimeter has a mode of resistance mode, because that's why it can measure directly resistance of anything. So we use the resistance mode and connect the thermistors to terminal with the multimeter. This is the circuit diagram we can see, and this is the setup that thermistor is directly put into water. And although there is some as water is not non-conductive, or if it has a conductivity, but it is very large, very small conductivity. That's why we can dip the thermistor directly into water. There is no problem. So this is our experimental setup, that one stopwatch. You can use mobile phone, one multimeter, one thermometer, and thermistor. And I have taken one beaker. You can use a normal pot to store water. So resistance of thermometer I have taken at theta equals to room temperature, means 28-degree temperature. You can see the thermistor showing for that thermometer the resistance is 105 ohm, but for different thermistor this value will be vary. To heat water, I have told how to heat water, and this hot water you have to put into a glass or some container, and uh, I have heated the water, and the heating hot water is kept into the glass, and that time at temperature 80 degree, you can, if you see carefully, you can see that the temperature is here 80 degree centigrade. At 80 degree centigrade, the resistance of thermometer reduced to 26.3 degree. 26.3 degree. Previous at room temperature, the sorry. At room temperature, the resistance was 105 ohm, and at 80 degree temperature, the resistance is 26.3 ohm. Mm, so I have taken time, temperature, and resistance data for the both experiment, calibration of the thermistor as a temperature sensor, and to verify the Newton's law of cooling. You can see with increasing time, the uh, hot water temperature decreasing and resistance of the thermistor increasing. Okay, I have just showing you. You can see the temperature is gradually decreasing and the resistance increasing with time. You can see around 74 degree temperature now. The resistance is 30.2 and the time left 1 minute 25 second. Okay. So I am just going to show the data I have taken. The data I had at temperature 80 degree centigrade, the resistance of thermometer was 26 ohm, and when temperature gradually start decreasing, resistance of the thermistor increasing. Very simple experiment, and after that I have the temperature of Kelvin scale calculated, and 1 by T and ln R data is here given, and delta T is the T minus T naught, means temperature difference between surrounding temperature and the temperature of the water, and time elapsed time is here in second also, and ln delta T is calculated. So these are the data I have taken from this data, and again to verify this data, or to my calibration is accuracy, to verify the accuracy of my calibration, I have put in the thermistor into a ice bath, and that means its temperature is now about 0 degree centigrade, and its resistance I have taken that 345 ohm. And if I draw the graph, I have drawn this graph by origin software. You can draw in your graph paper also. Then if I draw a graph, and I have taken data between 40 degree to 80 degree centigrade, this is 40 degree and this is 80 degree, and I have verified that at uh, ice point or at ice bath, resistance I got 345 ohm, and if I convert it into LNR, I got 5.84, and after plotting on this graph, I got a most accurate data. The temperature given 273.22 Kelvin. That means around 0.22 degree centigrade. This is most accurate. So this is the graph. After that, I have verified Newton's law of cooling, that ln theta minus theta naught versus time graph. This graph also a straight line, and the slope of the curve is given here, that 92 into 10 to the minus 5 per second. So Newton's law of cooling verification is done by this way, and after that I have uh, done this experiment below room temperature. So to do the below room temperature experiment, I used some ice and put in a thermistor and thermometer into the ice bath. And when after melting the ice, the temperature start increasing to up to room temperature. And during increasing the temperature, I have taken the temperatures versus resistance and data. The data below room temperature is here. When temperature is 7 degree, resistance is 280. Resistance is 266 ohm. And gradually with increasing temperature, the resistance decreasing. Again, I have drawn 1 by T versus LNR data um, graph, and here I have put all the data from 80 degree centigrade to 6 degree or 7 degree centigrade. I have taken 7 degree, all the data, and I have drawn the graph. And from that graph, uh, I am able to found the beta. Beta means the value of the coefficient. Beta is this is the beta um, constant for this thermistor. So the value of beta is about minus 204.255, as it is a NTC thermistor, negative temperature coefficient. So the beta is negative. For PTC thermometer, beta will be positive. Okay. So this is the calibration of my thermistor. It can be used from 0 degree to 100 degree easily, and it will provide more accurate data. So I am going to show you some data from origin I have taken. This is my graph. If I put any resistance here, okay, it will show the temperature in degree centigrade or anything. Say if I put some resistance 50 ohm at particular temperature, it will show that LNR will be 3.95. Mm, sorry. Sorry, sir. Sorry, it is not showing now. But if I put 345 ohm at 0 degree centigrade, then LNR is given here 5.84354, and one and then 1 by T is from this graph. From this graph, 1 by T is given here 0.00366, and from that graph, T is taken as T is given as 273.30026. That means its temperature now it's showing at 0.30026. Okay, above room temperature, it that's showing above room temperature, the calibration above room temperature, the graph showing the ice bath, that means at resistance 345 ohm, temperature is 273.22 Kelvin. But after full calibration, it's showing also about same temperature region. It's showing around 0.30026 Kelvin. That means thermistor is a most sensitive and most accurate. It can be used as most sensitive and more accurate temperature sensor. And I can verify also the Newton's law of cooling by this simple experiment and using these simple apparatus. Thank you.
So, are there any
Yes.
questions, Shinjini?
No, I don't see any question in the chat box.
Okay, so Deep, you have finished, right?
Yes, sir. I finished.
Okay, so I would like to make a comment. I mean, you see, I mean, it is about
স্যার
five.
এখান থেকে ব্যান্ড গ্যাপ বের করা যেতে পারে না স্যার?
হ্যাঁ, সেটা সেটা আসলে এই স্টুডেন্টরা এখনো এত তো শেখেনি, মানে সেই জন্য আমি আর ওটা জন্য কিছু বলিনি। ইট ইজ পসিবল, so let
Yes,
us
sir.
defer it for maybe another 6 months or something, when they will learn things like that. But my point is, I mean, it is just a 5 rupee component,
Yes.
and it is behaving so beautifully from 0 to steam point. I mean, this is incredible. It looks like incredible to me. Wonderful stuff, this thermistor. I mean, you see, I mean, if some friends, 10 of them, they buy a mercury in glass thermometer, so which is about 500 rupees, and with that they can calibrate each one of them a thermistor which can serve for the purpose of a good thermometer at home. Is wonderful. প্রথমে একটা থার্মোমিটার লাগবে to calibrate in a very good fashion. But once that is done, thermistor is wonderful. I mean, I never knew that it works so well below room temperature. I had seen its calibration curve above room temperature, but I mean, this he has done putting this thermometer in ice. So beautiful. I like this experiment. Wonderful.
Shrujit, should I add something?
Yeah, sure, sure.
It's a very nice material, and its
Yeah.
behavior is so nice. You have rightly pointed out it can be used as a thermometer in a nice way. My suggestion is
In every household, I mean, they can keep a digital multimeter, and this, of course, they have to spend for digital multimeter.
no. My suggestion is like this, slightly different.
Okay.
Suppose one or two, or someone has calibrated one thermistor and produced a calibration graph. Now let someone else take it up and need not measure the temperature, but measure the voltage and measure the resistance. Measure the resistance at different temperatures. Now he can use that calibration graph and check what sort of temperature is there. And of
No,
course,
but yeah, that is okay. Go ahead.
and I know one is different from the other.
Yes, that is the point. I mean, I don't know whether yeah,
Yes.
each one has to be calibrated.
Yes.
No, I understand. But can you please tell me how much is the deviation?
Deep,
Yes, sir. But I have not checked with the galvanometer and ammeter and voltmeter with and voltage source, sir.
no. What he is asking is,
I'm not talking about that.
he is asking is okay. Go ahead.
Now, suppose you have calibrated one thermistor and
Yes, sir.
you are providing me that calibration curve. I'm using a different thermistor. I know that is not the calibration curve for this one. But if you resistance and try to how far will be the
Sir,
deviation?
voice is not coming clearly, sir.
Dr. Chakraborty, you can devise one corresponding law of correspondence. Okay, but they are not equivalent or equal. One thermistor may have some correspondence with the other, so far temperature may be concerned, but they are not identical.
No, I mean, Manchi, identical no. আমার প্রশ্নটা হচ্ছে, suppose I get a calibrated, I get the data from a thermistor, and I
Yes.
use that calibration graph with another thermistor. Normally, the deviation, normally there will be deviation. I understand.
Yes, sir. There will be deviation also.
What is the extent of deviation?
The point is, he has not checked that. He has only one thermistor with him.
No,
The deviation,
they are different, quite different.
the deviation because of I think the material is used to make the thermistor and
But I think they can be normalized. They can be normalized, I think.
And I liked his graph, logger versus 1/t. I mean, this is so beautifully falling on a straight line. It is an experimentalist's pleasure to see such beautiful calibration graph.
So my suggestion is that all of us know with a calibrated thermocouple, we can measure the temperature.
Yes.
Yes.
It may not be possible that way here, but that's what I was interested to know the extent of deviation. Maybe we are taking the from the same lot. By lot, I mean with the same specification as it was written on the thermistor, and we can check what sort of deviation is taking place.
Actually, thermistor property depends on the material, not only material, the content of the material. How much material is there? So that is the problem. And for a thermocouple, only the two metals are rather
Right,
useful.
I understand. I agree. I agree. Just I'm interested whether anyone has checked the extent of deviation and how
And
much.
I have checked to some extent. They are quite, even if you take two thermistors at the room temperature, they will have different resistance.
Okay. Take it.
Will there be any guiding principle for the kind of standardization which Dr.
Yes,
Chaudhary is
that we have
referring to?
that we have to see. That we have to see whether you can. That I am telling. You can divide some
Professor
law
Samanto,
corresponding states also. You can
I
divide some
am
law also. Not only that, as we are used to do rather the corrections, temperature correction. Mind that can be done here also. In the platinum scale thermometer, we are used to make some corrections. That correction can be introduced here also. A
it's
lot
not
of
the
things can
question.
be done.
No, Professor Shamanto, perhaps it is a question of standardization. I'm giving an analogy. Maybe it may sound to be a very crude analogy, but see whether it is anything meaningful. See, when we used to draw the d lambda curve using spectrometer, so you are
Yes.
doing at your college, I am doing at my college, but that can be used as a d lambda curve for neon or helium or whatever, or sodium, not sodium and helium, whatever. We don't mention the spectrometer because we are doing it at the minimum deviation position.
But the
Minimum deviation position is the crust.
prism,
Similarly, here, is there anything like that with by way of which we can standardize? I
but
was thinking.
Professor Ghosh,
But
if you done mu lambda curve, not d lambda, if you
mu of
put,
the mu of
if
the
you done
depends on the
mu
mu
No,
of
even d lambda or mu
lambda,
lambda, whatever. D lambda or mu lambda, whatever.
that depends on the
But
material
that
and the
becomes a
process.
calibration curve independent of the spectrometer with which you have
that's but
obtained it.
if you draw the d lambda curve, then it should be peculiar for a particular prism for which the experiment has been done, not for general any prism. Spectrometer is okay because it depends on the material of the prism.
It is a d lambda curve of the characteristic material when be
Yes,
it
yes, that I
helium or anything like that.
Of the prism.
The prism or the spectrometer does not come into play.
no,
No,
no.
spectrometer is the
But
measuring device.
material comes into the picture.
Spectrometer is the measuring device. That's all.
Yes, yes.
Okay, ठीक है. I understand it's a very interesting device, and well, a number of things possibly can be done with it. Thank you, Dityanan. Thank you very much.
Thank you,
And
sir.
and I had another small comment. I think as Shurujitda has also hinted that our students will not be aware of this mathematical relation. So I think one point you should mention that this beta is a constant which is the dimension of temperature.
Yes, that I also was going to tell Deep.
That is very important. It is coming in the power of E. So
Yeah, yes,
the
yes.
power of E should be like
Dimension of
any
the
other power. It should be dimensionless. So beta should have the dimension of temperature. That this
Yes,
much information
Yes,
should
sir.
be
Yes,
conveyed.
sir.
But it's an excellent experiment. And
yeah,
I'm really very impressed. It's an excellent experiment.
yeah. I never knew. I mean, this thermistor behaved so. I mean, beautifully. I mean, there is not
And
much.
I must compliment Mr. Ghosh and Shurujitda and Professor Shamantaman. It's an excellent experiment.
Yeah. Okay. So.
Okay. Yeah, since we don't have any more question, maybe we can wrap up for the day. But before that, I want to thank Narayan Ghosh sir for his wonderful presentation. It was really excellent experiment. What we can try also at colleges also we can try to do it. So hope the students are now highly motivated to try these experiments at home, maybe with the help of their college for some of the experiments. And their lookout about physics practicals must have been changed by now. shifting from an exam orientation to learning physics by designing and doing experiments in unconventional and different ways, which demands a deep understanding of the subject. So, lastly, yeah.
Just one cosmetic modification. Mr. Ghosh, just go to the title of your experiment. Calibration. Well, this is just a cosmetic comment. Calibration of a thermistor as a temperature, because you have written verification. Calibration of a
Yes.
thermistor as a temperature sensor.
Yeah. All these points
Calibration,
should be indicated to absolutely newcomers to this field. Probably the first time he's giving a talk like this.
Yeah, but anyway, it was really wonderful.
sir.
Yeah,
But they are
it
doing
was
very
really
good.
very good. Yeah,
They are doing very good experiments, physics experiments.
Calibration off.
Yes.
Calibration off. Calibration off a thermistor.
So,
Thank you, sir.
yes. Okay. Now I think maybe we can wrap up for the day and we can discuss it also personally. So now I express my deepest gratitude towards the resource persons who took this challenging job of designing and performing these experiments and finally presenting them in a very lucid, detailed, and interesting way before us. Hopefully, the students as well as the faculties who are present here have learned many things from these 2 days. Another day to be continued. So again, we will meet on 2nd December. It's a Thursday, since the students will have college. So we will start sharp at 7 p.m. So I hope to see you, the students, again. And I thank you, the participants, also for giving their time with us and they want to learn something from here. So thank you all. Thank you all.
Good night.